All right, think back to algebra class for a second. It was probably a blur of x's and y's and a bunch of formulas you just had to memorize, right? But what if I told you one of its most famous problems wasn't really about numbers at all? Today, we're going to pull back the curtain and reveal the hidden visual world behind the quadratic equation. Seriously, forget formulas for a minute. What if you could solve an algebra problem just by looking at a picture? It sounds kind of wild, but it's a very real, very old method, and it shows us something amazing about where math actually comes from. So, here's our mystery for today. An equation you've probably seen a million times. X squared plus 21 equals 10x. Normally, you just jump to the formula and get an answer, but not today. Today, we're going to treat it like a puzzle. And that puzzle brings up some really big questions. I mean, why do these equations so often have two different answers? And why is the formula we use to find them so complicated? Well, it turns out the answers aren't hiding in the symbols, they're hiding in the shapes. So let's try something completely different. We're going to take this equation, and for a little while, we're going to throw out all the abstract symbols and try to solve it using nothing but simple geometry. Okay, so on the left, you've got the classic textbook method, right? Shuffling symbols around until you get an answer. It works, sure, but does it really tell you why it works? Now on the right is our approach today, solving with shapes. It sounds more like a riddle than a math problem. Let's see where this takes us. All right, let's actually do this. It's time to get our hands dirty and build the geometric proof. We're going to construct the answer, literally piece by piece, just like a jigsaw puzzle. First up, we need our main character, x squared. So let's picture that as an actual square, with sides that are x long. Easy enough. Next, the equation says to add 21. Okay, let's just imagine sticking an extra area of 21 onto our square. So this whole shape we've made now represents the left side of our equation, x squared plus 21. Now, according to the rules of our equation, the total area we've just built, that x squared plus 21, has to be equal to 10x. But what does a shape with an area of 10x even look like? And how in the world does it fit into our puzzle? Well, here's the clever bit. We're going to take that 10x and split it into two identical rectangles, each with an area of 5x. Then we attach them to the sides of our original x squared square. See how it makes this kind of L shape? Okay, take a good look at the shape we just made. We are so close to having a new, bigger, complete square. There's just one piece missing, right there in the corner. Can you see what size it needs to be to finish the picture? Right. That missing piece has to be a 5 by 5 square to fill that gap perfectly. And a 5 by 5 square has an area of 25. So let's slot that piece right in. And boom, we have now officially completed the square. Now that our construction is complete, get ready for the big reveal. Because the answer to our original equation has been staring us in the face this whole time, hidden inside the picture we just built. Okay, here it is. This is the aha moment. To complete our big square, we needed that corner piece with an area of 25. But think back. Our original equation only gave us an area of 21. That difference, the gap between the 25 we needed and the 21 we had, that's the key to everything. It's just simple subtraction. The area we needed was 25. We subtract the area we started with, 21. The difference is 4. But listen, that's not just a number. No way. That is the area of a small, hidden square that makes this whole geometric puzzle work. So let me ask you a simple question. We have a square, and we know its area is 4. So what is the length of its side? And here's the twist. The square root of 4 isn't just 2. It can be positive 2, or it can be negative 2, because negative 2 times negative 2 is also positive 4. And just like that, you're witnessing the geometric birth of the two solutions. And this is where it all clicks. The side of those big rectangles we added was 5. The side of that little inner square we just found is 2. So the geometry tells us our unknown length x must be 5 plus 2, which gives us 7, or 5 minus 2, which gives us 3. And there they are, our two solutions, 7 and 3, derived from a picture. But it gets even cooler. This visual game we've been playing isn't just some party trick. It's actually the secret origin story of the famous and, let's be honest, often feared quadratic formula. The entire method works because of this core idea called the difference of squares. The solution literally came from the difference between the two key square areas we found. The big one we needed to build, 25, and the piece of it we already had, 21. Now check this out. Every single piece of our geometric puzzle maps directly onto a piece of that scary formula. That half the rectangle's value of 5, that's just b over 2. The area of the corner piece we added, 25, that's b over 2 squared. The area of that small inner square, 4, that's the whole b over 2 squared minus c part. Suddenly, the formula isn't a random string of symbols, it's literally a set of instructions for building squares. And that key number we found, the area of that small square, the b over 2 squared minus c part, that has a special name. You've just witnessed the birth of what mathematicians call the discriminant, and it's the absolute heart of the quadratic formula. And our picture shows us exactly why this discriminant thing is so important. If its value is positive, like our 4, you get a real square with a real side length, and that gives you 2 solutions. If the value is 0, the square basically vanishes into a point, giving you just 1 solution. And if it's negative, well, you can't build a square with a negative area. It's physically impossible. And that's why there are no real solutions. It all makes perfect visual sense. And that's the real takeaway here. The complexity, the 2 solutions, the crazy-looking formula, it was never just abstract math. It was all, every last bit of it, coming from geometry. It really makes you wonder, doesn't it? What other mathematical secrets are hiding out there, in plain sight, encoded in simple shapes, just waiting for us to see them?